On the homework. 10.4 is due today. Which edition?
Second. Take a look at it.
Do you have the thing on your...
Yeah.
Number 11. Yeah, that's a weird one. I wouldn't worry about it.
Thank you.
That's the one where you have to like draw the vectors along the wall and sort of do the whole right-hand rule thing and sort of get cross-eyed while you're figuring out where the vector is going. Yeah, don't worry about that. The number 9 originally was assigned for actually the first edition, which I think is a more sensible, practical problem. Any other questions?
Yeah, number 31
In the second edition.
in that book, yeah.
Find a non-zero vector orthogonal to the plane through the 3 given points. That's actually a pretty important problem to know how to do, so we are going to do that one. What? Was that a sign? 31.
No, it's not a sign. 30. 30, it's 139 odd and then 33, 39, 46.
Oh, well, we can do 29 then. It's in the same.
But you said it's important.
It's important to know how to do it.
Right, if it's important, maybe we should do it anyway. I foresee an exam coming up.
We can do 29. It's in the same group. So it's find the vector orthogonal to the plane through. Okay, how do we do it?
Find vector PQ and PR, and then you get the cross product PQ and PR.
Right, so you think of these as just 3 points in the plane, like P, Q, R. You can find 2 vectors going this way, and then you just take the cross product, and you get something orthogonal. That's it. So we have PQ. And we can find PR. PQ is what?
Negative 3, 1, 2.
PR?
6, 1, 2. 3, 2. 3, 2, 4. Oh, PR.
So the vector orthogonal is just going to be Q cross product with PR. And what's the cross product here? So you have minus 3, 1, 2, 3, 2, 4. And remember how we do this? So we, for the I component, block out everything in the I and J component, and you have that little square that you do that 4 minus 4. Block out everything in the J. You get minus 12, minus 6, right? That's minus 18, and then you change the sign. Then block out everything in the K's column and row. Get minus 6, minus 3. That's the cross product. And that's it. That's the vector we are after. It's very important to know how to do this. In fact, today we're going to find relevance in that sort of exercise. We're going to be doing things.
And what's
We're
the
going
area?
to be using this. Come again?
The area.
There are 2 problems for this one.
Find the area of the triangle PQR.
That was the part I was
So this was part A. Part B. The area is actually equal to 1/2 the magnitude of that vector Q cross B. Which is going to be that each.
Or
Huh?
404.
Oh. It doesn't get to a 9. You could have made that a slightly nicer number. But you could have realized that this was 18 is 9 times 2, right? So this is just 2 squared times 9 squared plus 9 squared. You can factor out the 9 squared to get 9. And you're left with 5. So it's 9 over 2 radical 5. Other questions? In second edition?
Yes.
Okay, P is a point on a line that passes through a point Q and R. Show that the distance D from the point of the dot. Yes, in the second edition. We're okay with this, right? So I have a line that passes through 2 points Q and R. The distance D from the point P so the line is this, and QR, they say that this vector here is A, B is QP, that vector there is B. Show that D is equal to A cross B over A. Okay, thoughts? Did anyone attempt it? Yeah?
Project B onto A, and then you have a.
If you project B onto A, you get this magnitude here, or that vector here.
And then you have a triangle, and then you make a triangle, and you find, and then you find D using. Oh, you don't have the angle.
No, I mean, you could put it there if you'd like. Yeah, there's a right triangle here. Yeah?
So the magnitude of A cross B is equal to B sine beta times A. So if you just put A under the magnitude of A under divide or multiply by the magnitude. No, divide by the magnitude of A. Then you'll get B sine beta, which is the distance B, is equal to A cross B over the magnitude of A.
Right. Basically what he was saying, well, he's sort of going backwards. But this is, you know, again, quiz 1. D would actually be B sine theta. Right? And then that you just multiply and divide by the magnitude of A. Right? So this gives you A, B sine theta divided by the magnitude of A. And we know the top is actually just the magnitude of A cross B by the formulas that we had last time. And part B, now you just plug that in. Basically, in part B, your vector A would be QR. So it's just going to be minus 1, minus 2, minus 1. And your B would be, B is actually QP. I like to just write them right under and just do the cross product right here. You can set up the I, J, K. So your A must be equal to, you have minus 14 plus 5. J, you have minus 7, minus 1. That gives you 6. And that gives out minus 5, minus 2. Huh?
I think you miscalculated the J component. Shouldn't it be 1 minus negative?
It's,
yes, you're right, never mind.
right, minus 7, minus 1.
Yeah, okay. My turn.
Yeah, minus 7. Oh, these are two negatives. So it's minus 7, minus 1, which gives you minus 8.
But then it's minus J.
So it should be positive 8. Huh?
Minus 8.
Minus 8.
Because there are 3 negatives. Negative J.
Minus 7, which is 8.
Yeah.
No, it'll be minus 7 time minus, it'll be minus 7 minus 1, right?
Mm-hmm.
Which is minus 8.
And then
And
the
you
minus
switch the
J.
sign. So it's positive,
Oh, okay.
which is what? Yeah. And so now your D is just going to be the magnitude of that guy. Or the magnitude of A is the square root of 9 squared plus 8 squared plus 7 squared all over the square root. Plus 2 squared plus 1 squared equals whatever. Other questions? In which edition? Oh yeah, I shouldn't have assigned that because 30 we didn't do torque, and 39 in the first edition wasn't about torque, so just forget that. What was 30? I think 39 in the first edition was actually this, right?
Yeah.
Yeah. So this is actually 39 in the first edition, which is 45 in the second edition. Is that it? Okay. All right, make sure you drop off your homeworks before we leave for the next section. We're not going to do MATLAB. I'm just going to continue. I think Wednesday we're going to do MATLAB after we start being able to draw the surfaces by hand. We're going to use MATLAB to actually draw them on the computer. I think it'll be nice to see them. For now, we're just going to continue. Pick up where we left off. And I'll wait till we go to the next section to give you the quiz because it's the seating arrangement here seems weird. Yeah.
I had a question. When you evaluate that, you don't get the answer that you get in both. Actually, wait, no. If you, oh, because that's root of 6.
Yes.
That's one. Okay.
Okay, so what did we do last time?
We did calculus.
Okay, who can tell me what the equation of a line is without looking in the book?
R of t equals R naught plus t times the direction vector.
And R naught is what?
R naught is the location vector of a point on the line.
Right, this is a point on the line. And this is?
It is a vector parallel to the line.
Can you tell me another form for the equation of a line? X is equal to?
AP. What?
And what's X naught, Y naught, Z naught?
Direction?
Okay.
Oh,
This is the point on the line. Right? This is your R naught. Okay, what's ABC?
The
Direction.
vector.
That's the direction there. Right? So if you actually write the V as ABC and this as X naught, Y naught, Z naught, you can plug these in. And this guy you can think of as what gives the position a random point on the line. Then you can get to this. Right? What's this form called?
Vector form.
It's called the vector form. And this?
Parametric.
What's another form?
X minus x0.
Symmetric form?
Symmetric. Over. Equals y minus y0 over b. Equals z minus z0 over c.
Right, and this is called?
Symmetric form.
Okay. Right, you need to know this by heart, right? This is the equation of a line. Just like how facts in algebra, what's the equation of a line? Everyone can say y equals mx plus b, and what is b? It's the y-intercept. What is m? It's the slope. Like, just how you know that very well, you're supposed to know the equation of a line very well. It's the equation of a line, right? That's why. Okay. So, how do we know two vectors are orthogonal?
Their cross product is 0.
The dot product is
How do you know if they're parallel?
cross product is 0.
Okay. I define a vector orthogonal to two other vectors. Can anyone tell me a context where it's important to know what a vector orthogonal to two other vectors is?
Equation of a plane.
For the equation of a plane, I see someone's reading ahead. That's correct. We're going to do that today. Okay. So, let's pick up where we left off. Right, so I gave you that example. So now we're going to talk about line segments. The equation of the line that we just wrote down, those are equations of a lines that go on forever, right? But what if you only want like a small section of a line? How do you get that? That's called a line segment. So this is 10.5, continue. I'm just going to give you their formula. There's a formula that the book gives you. I don't know, I never remember. Or t goes from 0 to 1. This gives the line segment to the point 1. Okay. When t equals 0, we are at R0. When t equals 1, so basically this gives us the equation of a line segment. If we start at some point R0, we don't want to go on forever, but we just want to connect a line from the point R0 to the point R. This will be the equation of that line. You can see that it's not very difficult to see. If you plug in t equals 0, what happens, right? This point goes away, right? And then you just have 1 times R0, so that it gives you the point R0. If you plug in t equals 1, then this dies, and then you only have the point R, right? So 0 will start here, and 1 will end you up there. And because it's a linear equation, you move along a straight line when you hit one point to the other. Okay? When I'm sort of doing these problems, I sort of think of line segments in a different way. It looks more complicated when you write it out, but when you start practicing, I think it's actually easy. You can do a line segment in this way. For t goes from 0 to 1, set x equals can set x equals x initial plus x final minus x initial times t, y equals y initial plus y final minus y initial times t, z equals z initial plus z final minus z initial times t. This just says you start here at z, the initial point, and then you add whatever gap you have to move by to get to the second point, right? When t equals 0, you're at here. When t equals 1, you end up here, right? It's a very similar thing, but I sort of like this formula better because when you're actually doing it in practice, thinking of it in that way, it's sort of quick. It makes you look like an expert when you're finding a line segment. So, example. I guess I should probably show you both ways. Okay, so the idea of these are points, but we're going to think of them as position vectors, right? So if I want to use the first one, the formula in the book, how would it look?
You would have to find a vector first. I mean, yeah,
No, these points are the position vector. So it's 1 minus t times the vector 1 minus t plus t times the vector 1, 7. That would actually be it. But of course, you could simplify if you wanted to. This is just 1, 2 minus 3 minus t times 1, 2 minus 3 plus t times 4, 1, 7. So 3 plus 1. That'll be the equation of a line. What do you notice about this? Anything jumps out at you from that form?
It's just a standard vector form for a line.
Yeah, a point plus t times a direction vector. Notice that the direction vector is the same thing you'd actually get if you actually found the vector connecting the 2 points. It just so happens that you make sure that the first point was the initial point that you were given, and if you force t to go from 0 to 1, you actually will start here and end here by restricting t to go from 0 to 1. That's one way you can think about it. And if I wanted to find the parametric equation of this line, how would I do it?
X equals 1 plus 3t. I mean, that's basically your, right?
Yeah.
So I equals 2.
Plus.
Minus t. Z would be equal to
Plus 10.
plus 4t.
Ah, yes.
Right? Now notice here, these points here are the initial points, just like in this formula, xi, yi, zi, that's where you start. And this is actually the distance you move to go from the initial point to the final point, which you get from the subtraction. Now, look how you can actually, if you think of it in that way, look how quickly you can write down the answer, right? So, if you think of it in that way, and you want to go from 1 to minus 3, 2, 4, 1, 7. Here's how you can get to the line really quickly, right? You start by writing down the initial point, 1. Then you ask yourself, how much do I have to add or subtract to get to 4? 3. I need to add 3. Attach a t to that. Right? Y starts at 2. What do I need to do to get to 1? Subtract 1. Attach a t to it. Z starts at minus 3. What do I need to get to 7? I think this should have, you were right, that should actually be a 10. Because it was 7 minus a minus 3. And that would tell you that you have to add 10 to get to the 7. So you write down where you begin, figure out what you have to add or subtract to get where you're going, attach a t to that, and restrict t to go from 0 to 1.
So your answer, that's parametric form?
This is a parametric form, yes. When you say x is a function of t, y is a function of t, that would be. So this is the parametric form. But you can swap between any forms, right? So I can just throw this into the first component, the second component, the third component, that's the vector form, right? And then if I solve for t and equate all those, I can get this symmetric. So questions will ask you for different things. Sometimes the question will specifically ask you, write the answer in this form, right? And if it gives you in any one of the forms, you should know how to deal with it to get to another form. But that's all there is for line segments. Now we're going to play around with lines a little bit more. Finding line segments is especially useful in 392, which is linear algebra and vector calculus for engineers. You find line segments all the time. You're doing something called line integrals, but so don't forget this for anyone going on to 392. How do you know two lines are parallel?
Cross product is 0.
Can't say the cross product of lines.
The scalar product of each other.
They don't have any
Absolute value.
That only applies to vectors.
Can you choose a point on the line and then take the cross product?
vector is equal.
Same.
Their direction vectors are parallel. Parallel is 1R, right? And how do you know if two vectors are parallel?
Scalar multiples of each other.
One is a scalar multiple of the other, correct, right? You don't have to like do cross products or anything. That's, you sort of want to avoid cross products if you can, because they're annoying. Okay, so if their direction vectors are parallel, if two lines are not parallel and they don't intersect, they are called skews. So we know two lines are parallel if their direction vectors are parallel. If they're not parallel and they never intersect, we call them skewed. We say the lines are skewed, or these are skewed lines. Okay, so as an example. Determine three examples that we're going to work through, and then we move on to planes. So A, these are the pairs of lines. L1, our first line is technically I don't want to use the same parameter for these guys. Don't put a T. Put something else. Like, well, what's your favorite letter?
S.
People always mix that up with a 5. You want to use S? I have S written on my example, but then people always mix S's. Okay. Let's go x equals. me sure I write this down because I'm half asleep. 6 times 3. Okay, that's it. That's right. How do we tackle the first one?
The first one's a parallel,
How do you know the first one's parallel?
because the direction vector for line 2 is double the.
Right, so the direction vector for line 1, let's call that V1, is minus 3, 2, 4. The direction vector for line 2,
6, 4, 8.
minus 6, 4, 8. That's actually just 2 times minus 3, 2, 4, which is 2 times V1. Lines are parallel. Do they intersect?
No, they're parallel.
Lines can parallel and intersect.
Wouldn't they be skew then?
Give me a point that the first line passes through. If they're parallel and they intersect, what happens?
Are they the same line?
They're the same line, right? Just written in a different form. Right. So, what's a point for the first line? Huh? A point on this guy would be 6 minus 2, 5, right? Just plug in t equals 0. Easy to figure out. What would it be a point on this line?
10, 3, 7.
Will there ever be a point where will there ever be a case where those two would actually end up with the same point?
Yeah, if one is going this way and the other is going this way.
Could you plug in a t value here such that you'd actually get 10, 3, 7? Well, let's check. What would you have to plug in here to get a 10 in the x coordinate? Negative 4 over 3, right? So to make the x 10, you need t equals negative 4 over 3. If you plug in negative 4 over 3 over here, what do you get? Doesn't matter. It's a negative number, which that's a positive, right? So we know that they will always go along two different sets of points. Because one, they're parallel, and this one will never touch that point. So they're separate forever, right? So they don't intersect. Well, the direction vector for here, V1 is in this case is what? And V2 is? not parallel. Do they intersect? It's sort of easy to check with parallel lines if they intersect or not, but with in general lines that are not parallel, it's sort of more complicated. But how do you find intersection points in general? Set each component equal to 0, right? They intersect if the x coordinates coincide at the same time the y coordinates coincide at the same time the z coordinates coincide. So let's do that. Check intersection. Set the x, y, and z components. If the x's are equal, what do we get? And if the y's are equal? The y in the first line is 3. The y in this is 2s plus 3. The z's are equal. We have minus t plus 1 equals s plus 1. Okay. So there are 3 equations and 2 unknowns. We just have to make sure we can find 2 of the unknowns that satisfies all 3 equations. If that happens, they actually intersect, right? What do you think? Well, 2 only has actually 1 unknown. We can actually solve for s there. What is s?
0.
S equals 0. If s equals 0 in, say, 1, what would you get for t?
0.
T also equals 0. And in 3, if s equals 0 and t equals 0, does it make sense? Yes. Right? Because then you just get 1 equals 1, which is actually true. Right? So that's the idea behind, if you have only 2 unknowns and 3 equations, all you do is just solve it in one pair and then check that the solution works in the third line. And so, yes, it will actually intersect. Can you find the point?
T and 0, T and S equals 0 at the intersections. We just plug that into parallel, which is what we have.
Yeah, plug it into either one of those lines, right? Plug in either t equals 0 into the first line or s equals 0 into the second line. You should get the same point. That's what you solve for. Plug in t equals 0 in L1. Or if you'd like, s equals 0 in L2. The point you would get is x equals, if t equals 0, x equals 2, y equals 3, z equals 1. So the point of intersection is 2, 3, 1. So these 2 lines actually intersect, right?
Can you ask, does it make sense in that breakdown? If s equals 0 and t equals 0, does it make sense?
Does it make sense? Yes.
Just
Do these solutions make the third equation work? Because I found these solutions by using equations 1 and 2. I have to check that they actually make sense in the third one. Like if I plug them in, that equation makes sense. If it didn't make sense, it means there's no 2 pairs of solution that solves all 3. Right? So that would be. Last one. C. What's V1 and V2? V1 is 3, negative 1, 1. V2 is 4, 1, minus 3. Not parallel, right? How do I know? Well, to make the middle ones coincide, I'd have to multiply by a negative 1, but if I multiply by the negative, I don't get the other numbers. So it's not parallel. Check for intersection. So again, you set the components equal to each other. So we have 3t is equal to 1 plus 4s. We have 2 minus t is equal to s minus 2. And we have t minus 1 is equal to minus 3 minus 3s. There are 3 equations. Okay, solve it. How do you solve it?
Say S equals
Tons of ways. You can use substitution. You can solve for s or t and say this equation. That would be fine. Or you can solve for t in this equation. Try to avoid fractions or anything too complicated. Right away I saw that we could probably just add these two. Because I have a negative t and a positive t. If I take 2 plus 3, I would actually get 1 is equal to minus 2s minus 5. So this is 6 is equal to minus 2s, and s is equal to minus 3. Come again? And in 3, if I plug in s equals minus 3, I get t is equal to 1 minus 3 times minus 3. So minus 2 plus 9, that's 7. Are you right so far? And so check in equation 1. Now if I plug in t equals 7, I get 3 times 7 is equal to 1 plus 4, s would be minus 3, which is equal to minus 11. Contradiction, right? They do not intersect. Questions so far? Okay, so we've asked all the easy questions with lines so far, so we'll ask more complicated ones when we learn about planes. Take a 10-minute break, and we meet in 5108.